We are recording. So, yes, welcome to today's meeting in the Gemini Center on quantum technology. Just two words for those who don't know the center is that it's a loose organization, I would say, but still, a formal organization as a collaboration between different Norwegian institutes. With the goal to have different subfields talking to each other, even though the exact research they do might be very different, but where everybody does something quantum related. So the quantum community in Norway is quite small, so I think this is a very valuable thing to help grow it. So that people can collaborate. I mean, if there are possibilities for research collaborations, that's great, if there are open questions that some people don't know how to answer and somebody else comes in with new tools and stuff. But also one of the important reasons for this is to have collaborations on funding applications, center applications, and all of these things. So the center itself is, very small, led by 3 people on a voluntary basis, essentially, but we have a yearly budget of 10,000 euros, nothing. So that's essentially what we are. That is split into 3 tracks, which is the quantum computing track and algorithms. And then there's the hardware and sort of sensing and research. Research on how to essentially build qubits. So that's sort of the materials track, if you will. And then there's the track that I'm leading, which is quantum communication and security. So it's anything to do with interactive protocols, including, quantum coding theory, as well as cryptography, of course, both quantum cryptography, but also post-quantum cryptography. And we will see today that it's an example of post-quantum cryptography interfacing quite directly with quantum theory, which is sort of where we usually draw the line. Like it should still be a quantum flavor to the research, let's say. So if you just do LWE optimization, then that's maybe not as good of a fit for the track, because in Norway we have quite a close-knit cryptographic community, so I don't want to be competing with those organizations, if that makes sense. Okay, so if you have any questions about, let me know. That's essentially what we're doing here. Yes, so today I wanted to talk to you about something called group actions, which is a framework for post-quantum security. It is a quite general framework, but it is related to isogenies in that most of the group actions that we care about are constructed from isogeny-based cryptography. But they are, in a way, a generalization of good old group-based discrete logarithm problems and these kinds of things. So you can sort of port a lot of the old intuitions about discrete logarithm-based cryptography without having to care or understand that much about isogenies or really anything at all. If you ideally you shouldn't have to care about. So what's a group action? I wanted to just contrast and compare to good old groups. So let's see if I can get this working. If you have an element, let's say A in a group, and then in the old world, you can also have and now you need to correct me if I'm wrong, because I'm making some simplifications here, but we can view these both the exponents when we generate these capital letter elements. Okay, let's put this down here. as part of the same group, which will typically just be like Z, right? And the point of a generator, of course, is that you have some fixed G, which sort of has the feature that for all capital X in G, there exists a small x such that capital X equals G to the small x, right? So it generates the entire group. That's sort of the idea here. On the group action side, we have elements. So I still want to say that the lowercase a is in G, but now the uppercase elements is not part of the group anymore, but part of some set X. So in particular, there are no group operation between set elements, right? So there is nothing of the form like A times B. That is actually just work. But what we, I'll get back to what we do have. We have something of a generator here as well. So I've been using, I like to put a bar over the capital letter to essentially just show that this is a set element so that we don't start to do operations on them. And we have something of a generator here as well, which is often called the origin due to how, like, inspired by how it's implemented in isogeny-based crypto. So I like to call this O bar, right? And then it has this similar feature that for all, let's say, capital X bar in the set here, there exists a small x in the group such that, and now comes this group action, the namesake of the entire framework, because even though there are no, don't I have my laser project? There we go. So even though there are no group operations on this guy, of course, this is a group. So here we have a group operation. So this will, in fact, be written as an additive group, and that sort of works as you expect. But there is also an extra operation that goes from the group onto the set. So this is the famous group action. So what we're saying is that you can generate the entire set by having this X be operated onto this origin. And then you get your big X. Right. So intuitively, if you want to sort of use your intuition from discrete logarithms, what you have to imagine is that this guy that goes in front of this operation is the thing that was in the exponent before. Right? So we have some group operations, right? Classically, we have that if you have an A here, you can put a small b in the exponents. And then due to sort of this representation with the generator, you know that you get g to the a to the power b, which is usually written g to the a times b. And you have also an operation between these capital letter elements, right? Which is then g to the a times g to the b, which becomes g to the a plus b. Okay. For this group action, we get something similar. You can always do small b and then do the star operation onto some set element A. And thanks to our representation, we now know that this is the same as B star A star the origin, right? And then there is this essentially like a compatibility, I think they usually call it, which is the requirement that this should be equal to B plus A star O. And then I can also, since we're talking about this, mention that at least today we are requiring that this is also equal to A plus B star O. So that's what we mean by this being an abelian group action, namely that the group itself, is commutative. So this is also a good reason to why we might use or write in additive notation, because you usually think of the addition operation being obviously commutative. So I will not talk about non-abelian group actions or such things today. They exist, people are studying them. But this abelian group action, this covers the kinds of isogeny schemes like CSIDH, and more recently there is something called PEGASIS, which is in some ways a better instantiation of group actions than what CSIDH was. But I guess CSIDH is still more famous. Like CSIDH-based isogeny schemes and key sign and all of these things, they are not based on a commutative group, as far as I understand, and therefore they would not be covered by this very nice frame. So interestingly, this is also as an aside in this talk. Interestingly, because we have this commutative group here, this is one of those rare cases where we have, or I think it's actually the only case, as far as I know, where we have a post-quantum scheme where the best known attack is a quantum attack. I'm not going to, so you could say that, okay, Grover's attack is the best attack on AES. I would disagree until and unless somebody comes with, an implementation of Grover's algorithm that is more efficient than brute force search on a classical computer, which is just not the case right now. And I don't think it will be for 100 years. Maybe 50. For abelian group actions, you can sort of intuitively see why there would be a better quantum tactic, because it's exactly the abelian groups that are broken by a short algorithm. In particular, short algorithm solves this problem called the abelian hidden subgroup, whereas the non-abelian hidden subgroup problem is still quantum hard, as we know. But still, because this is operating on a set and not on a group, we don't get to implement Shor's algorithm. There is a different algorithm called Kuperberg's algorithm, which runs in sub-exponential time, whereas the best known classical algorithm is the exponential time. So this is kind of why for CSIDH and stuff like this, you actually have to implement them with quite large parameters, which makes them quite inefficient and leads to other problems involving, finding the group structure and things like this. Let's see. I was going to finish that thought, but it escaped me. But yes, what I wanted to say is that it is very similar to RSA, right? With RSA having a sub-exponential factoring algorithm, and therefore, for the security, you typically use 2048 bits integers instead of 128 bits, which you might expect if the best known attack was brute force search. All right, moving on. This group action framework allows you to do something that we can't do with other post-quantum primitives like LWE and stuff, which is to implement good old Diffie-Hellman. So just to recap how it works, right? Alice over here, she makes this A, which is G to the power A, and sends it over. Technically, this is, a static public key, so you can imagine she posted it on the internet. and Bob does the same. And then we get that she does calculate the key as b to the power a, which we now know is g to the b plus a, which crucially has to be equal to g to the a plus b, because this is what Bob is going to calculate. Right? That makes some kind of sense. Of course, the problem with this thing is that now this guy comes and breaks the entire thing. But we're good because now we can do this with group actions. So we have this origin O, right? So we apply this A to this origin O, and this gives us capital A. And this guy applies B to the origin O and sends it over. And then the key is calculated as A applied to B, which is, as we saw earlier, A plus B applied to O. And then we get that this is a commutative group action, which is why this works, which is the same as B applied to A, which is the same key. So here you really see that this commutativity is sort of the crucial thing that you need in the underlying group, which is also why you don't get as easily, I think, isogeny-based Diffie-Hellman schemes from non-commutative groups. So we had SIDH at some point, right? We used a more complicated setup and we're breaking the entire thing. If I
Yes.
There's others. Yeah. Okay, great. I don't know isogenies. I know this. Yeah. There's also something like Schnorr's zero knowledge protocol, where you can sort of ask the question, can you get everything from the D-log world by just going to group actions? And I think this is a neat example of where this actually fails. So for a classical Schnorr protocol, you sample some random message from the group, and then you calculate G to R, right? This guy over here is, you should only have A. This is a verifier, prover and verifier. So there's no secret for the verifier. But he samples some C from some binary set power lambda. And then Alice over here calculates C, which should be equal to R plus A times the challenge C, I believe. And then in order to check that everything works here, the verifier just calculates G to the Z, which should be G to the R plus A times C, which should be R times like this, R times A to the power C, and it knows both A and R here, so this verification can go through. And then, of course, you have to prove security, like you have to prove the knowledge property, you have to prove the soundness property, but all of these things are quite simple for this very simple program. But in this setting here, what would you do? Okay, you would start by sampling a random element from your group again, and then you would calculate R star, the origin, right? And then this guy would sample 0, 1, to the power lambda. And then now you're supposed to calculate this z here. And that's r and, you know, some kind of operation that is not defined, and a plus c, you know? And in particular, if you try to do verification later by kind of what you would want to do is, you know, C applied to the product of R and A, then you can see that this thing here is undefined. There is no multiplication between these elements. This doesn't work. There is a way to fix this, which is thankfully quite simple, which is that you do just a binary, like a single bit here, and send it over, and then you can see that you sort of just put a plus there, and either this term or you don't, and then verification is sort of checks which of the two cases for either c equals 0 or c equals 1. The problem, of course, is that then you get soundness 1/2. So with probability 1/2, an evil prover can fool the verifier by guessing the correct bit. And then you need to do soundness amplification, which leads to very inefficient schemes, essentially by repeating them a bunch of times. But it's possible. But the straightforward, simple thing doesn't work. So you can see that you get some of the things that you want from classical D-log world, but not all of them. So there's me scratching my head. Okay. So the topic I've been looking at recently is these generic models for groups and for group actions. So in the generic group model, you essentially, let's see here, let all group operations go through oracles. Right? And the way you do this is essentially that you reach G, you write some kind of representation of it, which is just, you know, a random bit string of some length, so that you can't operate on it, because then you would have to find the other correct bit string, essentially, so that you have no choice but to go to the oracle, which knows all of these representations and can calculate. This is my very high understanding of what is going on. Okay? And this is very useful in the sense that you can prove lower bounds, prove that D-log and CDH and DDH and so on are hard. And you do this essentially just by doing oracle queries, right? So you assume that, and crucially, adversaries are unbounded. So they can run in exponential time. But the time that you are counting here is the number of oracle queries that you are performing in order to perform your or to calculate your D-log. So then, in order to prove that the discrete logarithm problem is hard, you just prove that it needs exponential or superpolynomially many queries to this group operation oracle. Right? So you can do this for generic group actions as well. So remember that we have something like A plus B star, okay, let's say X, some general thing, right? But now, since we are in a post-quantum world, making operations on these guys is actually easy, right? With your quantum algorithm. So you don't necessarily gain anything by hiding the group structure. So we just leave this, like leave it be some Zn or something like this. But then anytime you want to perform this operation, you still have to go through the order. So this has not been the focus of my reading this week. So if I'm missing something or saying something wrong, you will let me know, right? Thank you. But there is one huge problem here. Big problem. So it's easy to define this, or easy-ish. It's straightforward, I would say, to define this generic group action model. But the problem is that D-log is easy.
In the quantum model.
Right. That is in the fully quantum model. That's better. Okay. So assume that you have quantum access to this. I need to use my quantum color then, which is this color. Thank you. So actually, I will be mostly concerned with the quantum models, right? And there is a big problem with the quantum generic group action model, which is that D-log is easy. So if you have quantum access to these oracles, there is an algorithm which is from the early 2000s, I think, which solves the D-log problem in polynomial many queries. So poly queries, but still exponential time, which is confusing in the sense that, okay, how should we interpret this result? Well, there is, let's say, the problem, right, is that this is conjectured exponential time. There is a problem that needs to be solved after the polynomial of many queries, which is sort of like a geometric. And the best algorithm we know for solving this problem is exponential time. But if you want to prove security of the D-log or CDH or whatever in this fully quantum model, you can't do it anymore, because what you're now doing is just reducing it to a different problem, which may or may not be. So it's a reduction, it's not a proof anymore. And some, potentially including myself, would say that sort of defeats the purpose of the generic group action model in the quantum world. Like one of the main benefits there is that you can get unconditional results, or in other words, that the only condition is that you are an idealized model, But still, it might be useful for security proof if you have the understanding that you are reducing everything to something which is conjectured to be exponential. And this is in particular something that Mark Zandri has been arguing, for those who know who he is. And he proves the security of public key quantum money, one of those very esoteric, classically impossible quantum cryptography schemes. So what I like about public key quantum money and schemes of that sort is that it is classically impossible, and it does not claim that its main benefit is unconditional security versus computational security, which is what the only thing that QKD has going for it, And in my opinion, this is a very weak novelty claim. But even though it's a full protocol, don't get me wrong, but it turns out that if you combine the world of quantumness and not knowing and all of these things with computational hardness assumptions, then you can build some pretty nifty protocols. And this is one of those. So he proved the security of this in this fully quantum generic group action model. But again, it's not unconditional. It is reducing to this, it's called the TAP problem, which is trigonometric approximation, I think. I don't know how to pronounce trigonometric. Trigonometric. Yeah. So that's the generic group action model. There's also an algebraic model, which has been the focus for this week. And in the classical setting, what you do is that whenever A would output some, capital X in G, have it instead outputs this X in brackets, which is sort of an explanation, like the group element itself, together with an explanation for how they constructed this group element. So it's X, and then there's some small x here, such that large X equals G to the power. Right?
Linear combination.
Oh, yes, I forgot. So there should be so this is a vector. Yeah, and then also you need yeah, okay, so this is a vector over all sort of previously seen group elements. So you get capital X is equal to the product then of like all of the previously seen ones, xi, to the power x vector. And then this would be I plus n plus 1, I guess. This is sort of what you do. So essentially you're saying that, okay, you start by some kind of input. It could be a couple of basic group elements. And every time you construct a new group element, it needs to be constructed from those previously seen inputs, essentially by exponentiation. Right? So this is also something that makes perfect sense in the algebraic group action model, where you get actually something which is a little simpler. So you have this set element now, together with some small x, and this can, of course, be and then I'm forgetting an index. So this could be, x0 up to some xn, like in the classical case, but it turns out that it's enough to assume then that this is a sum of those elements. And that's because, once again, that this product here is not defined over these capital X. So to complete the thoughts, you get that this capital X is equal to some previously seen element xi, and then this small x up to it. Right? So this works, straightforward. You can prove things in it. Now, crucially, this algebraic model here is weaker. Should do like this. It is weaker than the generic group action model in the sense that you can't prove lower bounds because there are no oracles here, so there is no oracle to count queries to. But you can prove reductions quite straightforwardly in many cases. So you can, for example, prove that CDH is equivalent to discrete logarithms, which is not known in standard model for normal groups. as it turns out, it is actually known to hold unconditionally for group actions, which is surprising to me at least. But you can prove other kinds of equivalences as well. One that we've been interested in is, this strong Diffie-Hellman, for instance, which you can also reduce to discrete logarithms. And that I'm pretty sure it's not known inside a model for either case. That would surprise me. And of course, you can write your security proofs in the Algebraic Group Action Model. So then, of course, you reduce to the underlying hardness assumption, which, since most of these end up being equivalent to D log anyway, means that your security proof can now reduce all the way to the discrete logarithm problem of these group actions, which is very nice. Okay, but just like with the generic model, what I'm interested in, mostly because it's fun to think about, is the quantum algebraic group action model. So there is a previous work here. One of the authors is sitting in the room, so this is why I keep asking her questions. And they defined the quantum algebraic group action model in the following way. So you have some x bar, and this is now understood to be a quantum state. Okay? So the explanation of it will be some, I always put this caveat because it's important, like exactly how you model things, but these are technically quantum registers, not quantum states, but they are registers containing basis states, meaning that it will be some superposition of basis states that look like the element itself, some kind of exponent, and some I. It's sort of a straightforward quantum application of the algebraic group action model. And I guess that's the entire thing. You don't have more information than this. So I can put this up here, maybe. That looks like it should work, right? And indeed, you can prove stuff in it. Yes, all of the proofs that you expect to go through, they'll go through, with D log being equivalent to CDH and so on. So you have D log and CDH. You also have a quantum strong CDH, which I didn't explain what strong CDH is earlier, but intuitively it is saying that, okay, the computational Diffie-Hellman problem should still be hard, even if you're given an oracle that solves the decisional Diffie-Hellman. So it's saying that there is some kind of gap in hardness between decisional Diffie-Hellman and the computational Diffie-Hellman, that solving one should not allow you to solve the other. So sometimes you hear this referred to as gap CDH. They are technically slightly different, but related notions. And then that is this idea of the gap in hardness between these two problems. Now, this strong CDH, like I just said, the problem is defined together with an oracle. So it's an oracle problem, right? You have a DDH oracle. And so naturally, you can ask, okay, what happens if I make the oracle quantum? You get quantum access to the decisional Diffie-Hellman problem. And then you get exactly the quantum strong CDH assumption. And in this model, you can also prove that this reduces to good old D log. So it works for most cases. But then we have Marx-André. He's not happy. Marx-André doesn't like it. I think that's more or less like a direct quote from the paper, just paraphrasing. So I think he will be fine with me putting this on the internet. And the reason why he doesn't like it is that his quantum money scheme, which I mentioned earlier, It's quite a nifty thing, actually. Like, essentially, what it does is that, let's see, you start with something that is, just in zero state, and then some state like this, and then you put it in a uniform superposition over all A, and then you have A here, and then you have your big X here. So this is via, the QFT. And then you do an entangled operation from one to the other, so you have A star X. And now, since we have this, completeness of the generator, this is now a uniform superposition over all set elements and a uniform superposition over all group elements. So we can say that this is like star, and then measure A. I think it's in this order. Yes, it should be. No, it's in the. So you do another QFT. So if you didn't do this operation in between, you would then get back to the starting state because this guy goes both ways. But now you get some state, which is essentially, I need to think. Oh yes. Okay, so that I am so sorry. I should have prepared this. We do the measure A first. Measure A outputs. Then QFT on the second guy. So then we get this some star goes to something, It doesn't go back to the start. It goes to some kind of dollar state, which is your quantum banknote. This is how it breaks. So the setup is actually super simple. What is harder is verification, but what he goes on to show is that there exists a way for the public, for anyone, to verify that this is a quantum, like a valid quantum state, without learning the secrets that you need in order to construct these quantum states. And if I understand correctly, that would be this secret here, since that is the only thing I see that can be secret. But note that this is a very particular superposition state now, right? I don't know exactly what it is, but it is some kind of superposition state with a lot of very particular phases and stuff like this, and then there's a complicated verification algorithm. Now, if I require that all states like this are in brackets, so if you try to put brackets around all of these things, then there are some extra information to the right. And crucially, these guys are entangled with each other, right? So for each x, there is like capital X, there is a unique lowercase x. So these are entangled things. And that means that you get a very different kind of dollar state here. So I should say, like, it's not equal to, the dollar in brackets, which is actually well defined because the dollar is a set element, just a superposition over set element. But the dollar in brackets is a superposition over more than just set elements. It's a superposition over set elements entangled with their explanation. And so you get a very strange scenario where, the basic functioning and correctness of the scheme works in the standard model, but breaks in this quantum algebraic group action model. So this is why Martin doesn't like it. I think this is a valid complaint because you would expect for a good model that at least, the correctness doesn't change. Of course, security properties will change, but the basic functioning of the scheme should match the real world. And we see here that this is not the case. So this is why he essentially reverted to this generic group model. And essentially just accepted that, okay, we will have to rely on this strange, understudied, maybe, problem for our security proofs to go through. Meanwhile, I've been trying to think of, are there ways to, like, are there alternative definitions of this quantum algebraic group action model that would allow you to prove correctness of this scheme, right? So I don't have any good answers, but I have a few initial ideas. Can we fix this? And essentially, so I'm running out of time now, so I will explain this very briefly. But essentially, my thought was that, okay, what are we doing? So in the classical case, we have that x is, again, this itself. It is some exponents, and it is some I. So we are asking the adversary to show its work, right? A shows its work. And so I was thinking, okay, but if A is showing its work, can't we have it explain what it did to us in plain text instead of part of a big superposition state where everything is like entangled with each other? So what if we try to do an alternative representation, which is, you know, registers with basis states. I keep writing this because I'm annoyed that people get it wrong, just to be clear. But yes, we have some quantum registers that have basis states that now only involve the set element itself, much like in the standard model. And then we have some unitary operator, U, and then an I showing the basis state. And then the idea would be such that this new state was arrived at by applying this unitary U to this starting state. Now, this is a very naive thought, so there's a lot of problems with this. I'll list a few. Problem 1. X may not be a pure state. So, for instance, it's like the adversary could have performed some measurements before as part of generating this state, or alternatively, it could be entangled with other internal memory. Now, if it just sends us this state right here, and it is entangled with internal memory, from our point of view, it looks exactly as if it measured it. So it doesn't help to assume that the adversary only does unitary operations, because it can still entangle. So we're still stuck with these possibly mixed states. Okay, so what if we say that, what if we just accept this? Let's say, accept this and let U be what's called super operators. So a super operator is, it is essentially to mixed states what a unitary operator is to quantum states. You can think of it, a super operator as a unitary operator that also includes measurement or hidden entanglement or whatever you want to say. For the quantum information around this would be like a unitary operator where a subspace has been traced up. Okay, you can do this, but the problem is problem 2. Then U is non-reversible, which breaks at least one of the security proofs that I wanted to try to get through. So it becomes very hard to affect the state that you receive, even though you can't, even though you can read off what they did to arrive at this. But like, what are you going to do? If they're telling you that, oh, I just did some kind of sampling, are you going to try to resample it? Will this help you? Probably not. Problem 3, of course, is maybe the most important of all. which is that U is black box. The entire point of this whole exercise was to be able to extract these X's so that we can use them in our security and not have these capital X's be black box. So what you try to do is like you make some assumption, assume U equals, U n, U star, U n minus 1, and then U star, U 0. Something like this. And that you now require more information. The U star is what you expect it to be. It is the group action operator. And then you require that all of the other U subset somethings do not apply the group action ever. Okay, can you do something with this? I don't know. So as far as I've gotten right now is that if I make a much more restricted model where one, I assume that the adversary is completely unitary, it never measures anything. Two, I make sort of like a white box assumption like this on the unitary, which now has to be unitary. And three, I always require that these explanations are pure quantum states, so they are not entangled with anything else that is hidden away. Then I can prove things. This is now you're getting into a very restricted model. In order to make this even make any kind of sense, you would then have to have all of the other entangled registers be forwarded as part of this explanation. But if you do this, then I can show that some of the security proofs you expect to go through, and you sidestep the issues that Mark-Andrew has. So it seems likely that you might be able to prove something there as well. But now that the model is so restricted, it is no longer it is now just like fully incomparable to essentially most of the other models. So it's just like an alternative way to formalize. So that's essentially the ideas I've had so far. So with that, I'm going to say thanks. Questions from online or offline? Sorry for rushing towards the end there, but I mean, it's just ideas anyway. In that case, I may